morning. Welcome to Science Symposium 2019. This has been in the works for some 2+ years, so it's kind of exciting to be at this point, to be able to present the work of our labors. We're here at 533 Diversity, and we just want to welcome all of you who are out there. I hope you can listen to the streaming, and we're ready to start. We're going to begin with Marjorie Ray. Marjorie received her undergraduate education at Birmingham Southern College and the University of Alabama, where she earned a BS in biology and psychology. She also has minors in chemistry and the humanities. She's attended graduate school at the University of West Florida, Florida State University, where she completed her master's in biology with an emphasis in biochemistry and enzymology and physiology in 1982. Marjorie's past occupations include biochemist at the University of Alabama at Alabama Birmingham. Areas of research include organ culture, endocrinology, lipoproteins, ethanoids, membrane proteins, lipid, detergent interactions, and protein crystallography. Scientist loading team for the 6 NASA Space Shuttle missions, STS-75, 77, 95, 110, 111, and 107. That's quite a list. And 1 SpaceX mission to the space station. She's retired from science in 2014 and is currently studying philosophy, ethics at Oxford University in the UK. The Urantia book found Marjorie in 1976, and she has been a student ever since. An early mentor was a great inspiration to her. She hosted a study group in her home for more than 25 years, and she continues to participate in 3 online groups. As Marjorie enters her 7th decade, she hopes to be of more service to the Urantia book community. Marjorie, the floor is yours.
Thank you, Ralph. Good morning.
Good morning.
Thank you. Thank you, Ralph, for your kind introduction. My talk today is going to be about water. And it may seem a little bit disjointed because we're going to be moving back and forth between science and philosophy. So just bear with me. These are 2 of my favorite topics. And so just bear with me, and we will come to, hopefully, an enlarged understanding of just what a gift water is to each of us. First, let's examine the words in my title: water, truth, beauty, and goodness. But we're not going to start with water. Let's start with truth, beauty, and goodness. The word truth is defined in the Merriam-Webster dictionary as that which is true or in accordance with fact or reality. Now, the Urantia book differentiates between truth and fact, so we might want to say what we say in accordance with reality. The word truth is used over 775 times in the Urantia book, and I went through and I read the 775 of them, and these are the modifiers or the adjectives that tell you just how much truth there is. And I may have missed a few, but it's as exhaustive a list as I could pull together, and it was a fun trip to do that. Let's move on to beauty, which is the quality or aggregate of qualities in a person or thing that gives pleasure to the senses or pleasurably exalts the mind or spirit. The word beauty is used 147 times in the Urantia book. Goodness. Virtue, moral excellence, kindness, generosity, the best part of anything, essence, or strength. The word goodness is used 149 times in the Urantia book. Of the three words, it seems to be the one hardest to actually define. It seems to be more conceptual than either perhaps truth or beauty. You will have noticed as we went through the list that there were two words on all three of them that were italicized and underlined. Those are the only two descriptors that all three of the words share in common. Liquid water, the entire science of mathematics, the whole domain of philosophy, the highest physics of chemistry, could not predict or know that the union of two gaseous hydrogen atoms with one gaseous oxygen atom would result in a new and qualitatively superadditive substance, liquid water. The understanding knowledge of this one physiochemical phenomenon should have prevented the development of materialistic philosophy and mechanistic cosmology. Paper 12, section 9, paragraph 3. This quote has fascinated me since the first time I came across it. There's a warning in there, and I just couldn't make it all come together. I couldn't understand it. This was written in 1934, and dates are going to be sort of important during this talk. So what were we not understanding, or what are we still not understanding? It seems that perhaps in 1934, we had knowledge or fact, but did not understand what we had. Perhaps if we delve a little deeper into the words used, we will begin to understand. Let's look at, in the second sentence, it calls liquid water qualitatively superadditive. So let's look at qualitatively. It's an adverb derived from the noun quality, and it has two meanings that could both be used in the context that it's used in the quote. A peculiar and essential character, an inherent feature, or a degree of excellence, superiority in kind. Each definition adds a little bit different nuance to the meaning of the sentence if you go back and look at it. Phil, I can ask my friend Phil Calabrese, our mathematician in the room, for some help on the term for superadditive later during the discussion. But basically, it was a mathematical term that was advanced in 1925 by the mathematician Michael Fekete. He was originally Hungarian and became a really rather famous mathematician in Israel. It is a mathematical statement of the old adage, when something is greater than just the sum of its parts. But also think that perhaps it was the only extant English word that conveyed some of the meaning that the authors were trying to impart to us. Now, in the second sentence, it refers to liquid water as a physiochemical phenomenon. So what does physiochemical actually mean? It refers to physiological chemistry, in the domain, which is in the domain of science that is currently referred to as biological chemistry or biochemistry. It is simply defined as the study of chemical processes within and relating to living organisms. So let's look at physiology and try to pinpoint it in time. The word physiology was used in the English language first by James Furnell, who was actually more what we would consider an anatomist today. He described the spinal column. And then about a little bit less than 100 years later, William Harvey, or 100 years later, William Harvey, who was more interested in gross physiological processes like explaining circulation and respiration. And then fast forward in 200 years and we get to Schleiden and Schwann, who in 1838 put forward the first two tenets of cell theory. But in 1838, they were still sort of toying with the idea that something similar or spontaneous generation were still in operation. But it took Rudolf Virchow in 1855 to put that one to rest. Enough experiments had been conducted, and so he added the third tenet of cell theory, which is the basis really of physiology today. And so here are the three tenets of cell theory, which is all living organisms are composed of one or more cells. The cell is the most basic unit of life, and all cells arise only from pre-existing cells. The modern version today includes additional tenets like energy flow occurs within cells, hereditary information such as DNA is passed on from cell to cell, and all cells have the same basic chemical composition. Some people dispute a little bit because you have to decide whether viruses are life forms or not, because they don't really satisfy a lot of this. So there's often the virology people step in and say, hey, we're a little bit different here, but all in all, this is still the basis of physiology as is practiced by physiologists today. So let's look at the history of water and try to place it a little bit in time. Lavoisier discovered oxygen around 1778, and he named hydrogen in 1783. But it's Cavendish who actually discovered the composition of water sometime between 1781 and 1783. He had actually discovered hydrogen, but he didn't name it. He just called it a combustible gas. It took Lavoisier to actually name it. Water is actually found 264 times in the Urantia book. It's found in all 4 sections and in 85 of the papers. Over half the time, the word refers to physical water, like what's in your glass. Other times, it is used metaphorically, such as in the water of life. So the authors state that an understanding of the physiochemical phenomena in liquid water should have prevented the development of materialistic philosophy and mechanistic cosmology. Prevention is not possible without the discoveries of both the chemical composition of water and how it participates in the life process. So from 1855 until the 1930s, what was not being understood? Let's look at materialistic philosophy for a few minutes. In 1865, Frederick Lang published a 3-volume set. It took him 3 large volumes to define materialism and its effect on both the philosophical thought and societal development in 1865. He, in his opening sentence of the first volume, he says, the materialism is as old as philosophy itself. He also, as you get through his volumes, he makes a really amazing comment, which is, to think clearly about materialism is to refute it, which I find very funny, humorous. Anyway, it is a form of philosophical monism, which holds that matter is the fundamental substance in nature, and that all things are material interactions. Monism just refers to a singleness of concept, which means in this case matter, and nothing else, just matter. It is now expanded to include things such as the 16 elementary particles in the standard model of particle physics, and even things like mental states and consciousness, and we will talk much more about this in just a few minutes. So what about mechanistic cosmology? Mechanistic is relating to the mechanism or doctrine of mechanism, which was first used in the English language in 1884. The doctrine of mechanism is a philosophical term that in its older incarnation was referred to as universal mechanism. Universal mechanism held that the universe is reducible to completely mechanical principles, which at that time was motion and matter. But we had the scientific revolution, and so post-scientific revolution, a new cosmology emerged, which was all phenomenon could be eventually explained in terms of mechanical laws, natural laws that governed everything. Consequently, all phenomenon, past, present, or future, must be completely determined, if you could define it, by very set laws. And of course, cosmology is concerned with the universe as a whole, so you could define the universe, and it was both very reductionist, you got it down, and you would define it in terms of matter, and that it was going to follow these exact laws that you were being able to elucidate. So now let's turn to some of the chemistry of water and some of the physiological processes that involve water, and a recent report that gives water another level of complexity. This is a diagram that you might remember from 3 years ago that was part of my snowflake talk, but it's an excellent diagram. It talks about the two components that make up water, your hydrogen atom and your oxygen atom. It tells you that the hydrogen has 1 electron and that you have 8 electrons on the oxygen. That hydrogen is the most abundant atom in the universe, and that oxygen is the most abundant on our planet. It was really interesting to note that Stephen Lower in the 1990s, who's a really good physical chemist, he actually recapitulated what our authors wrote in 1934 in one of his, on both of his website and in a paper that he gave, which says, on examining what is known about the two gases, hydrogen and oxygen alone, it is doubtful that today's science, and this is science in 1990, would predict water, a liquid, could even exist. So they said it in 1934, but then it's recapitulated in the 1990s. And to be quite honest, I don't think it would change. It would be very different today. So let me use this cartoon called a Lewis dot structure to discuss the stability of the water molecule. As noted in the previous slide, hydrogen has 1 electron, while oxygen has a total of 8 electrons, 2 in the inner shell and 6 in the outer shell. The first electron shell is most stable when there are 2 electrons present. The next shell can have 8 electrons, which gives the most stability. Thus, when the 2 hydrogens each share this 1 electron with oxygen, all are made more stable. Each hydrogen has 2 electrons in its outer shell, and oxygen has 8 electrons in its outer shell. These shared electrons form what is called a covalent bond, and is a relatively strong bond, represented in panel C with the lines. But note that there are 4 electrons the oxygen does not share. Since they are not shared, they cluster more toward one end of the oxygen and pushing the hydrogens that are shared a little bit closer together. This structure results in many of the properties of water, including its liquidity. And so the bottom diagram shows the 4 that are not shared, and then the two covalent bonds. This is a little bit better representation of the actual molecule itself. It gives you another sort of conceptual idea of what the molecule looks like. Not that you're going to actually ever be able to see it, but so it's positive on the hydrogen side. That's the green that you see. And it's more negative on the kind of purple pink side, the oxygen side. So you need to think about the positive pole and the negative pole. And so this is called a dipole in chemistry. And because of this dipole, water is able to have what is referred to as another type of weaker bonding, which is called hydrogen bonding. And that means that water molecules find it easy to interact with each other. And here in this example, you'll see where the hydrogen of this one is interacting with the oxygen of that molecule. Now these bonds, these hydrogen bonds, are really very, very important. They give water so many of what are referred to as its anomalous properties. We all know that the statement opposites attract, and that's what's exactly going on here. The positive of the hydrogens are interacting with the negative of another molecule's oxygen end. These bonds are rather weak. They form and break at an alarming rate, some less than 100 femtoseconds. A femtosecond is 1/quadrillionth of a second. We're going to be discussing quadrillions here in a few more minutes, so we'll get a little bit better perspective on that. So now I'm going to show you a molecular dynamic movie of the formation and breaking of hydrogen bonds in water. Now this entire movie runs for 2.5 minutes. We may not watch it for 2.5 minutes, but it's been really slowed down because it really represents 1.5 picoseconds. Okay, and a picosecond is 1/trillionth of a second. Okay, so we've taken less than 2 picoseconds and we've elongated it out so that we can even see what is going on. So it's been really, really slowed down. This simulation is done at 700 degrees Kelvin, which is about 80 degrees Fahrenheit. That's a little warm for room temperature, but it is certainly well below basal body temperature. So this is, if you think about what's going on in your body, this rate is probably a little slow in this diagram. So it may take it a second to load. So we'll see if it'll come up, and hopefully it won't. So there's the counting over there of the picoseconds as it's going by. And you see the bonds, the purple, as they form. And some of them last longer and some of them last shorter. And y'all might find that music annoying, I hope not. But it's when you realize the scale that you're looking at, it's pretty, pretty remarkable. There's one getting ready to come in from the, I've watched this movie a lot, you can tell it's going to come in from that side over there, and you're going to see it as it actually forms. Here it comes. It's going to walk sort of into the frame, and there are other ones that form and break even faster. But anyway, I thought this was pretty amazing to realize that you're looking at such a really tiny slice of time, and it's elongated it out so we can even relate to it. Because otherwise, I don't think we would be able to relate to it, right? So. If y'all really like that, I'll play it for you during the discussion. Okay. So let's turn to some other interesting information about water, and hopefully this is going to feed right into Ralph's talk later on today. In liquid water, water molecules are connected within an extended dynamical hydrogen bond network, which we saw during the movie, with the individual hydrogen bonds varying between being shorter, which are straighter and stronger, and then when they are longer, they tend to be a little bit more bent and a little bit weaker when they're longer. But I'm using these terms stronger and weaker and bent and all that. This is really actually a very narrow range. But one would readily argue that this rather weak, flexible, dynamic bond is how life even exists. In this diagram, here, let me get my pointer. The line that I want you to look at is just the red one, which is viscosity. We have all these other things, and what it's showing is that if we change the percent change of the hydrogen bond strength, how much change in the physical property they'll have to be, and these are done in percentages. So like if you only change the hydrogen bond strength by less than or negative 4%, then you're going to get a 50% change in the viscosity here. And then over here, it takes even less, only about a 2 or a little bit less than 2%, to get a 50% change in the viscosity here. Let me get back to my... now, understand that this change, like on the one, to the 50% change going down on the negative, that it takes less than 0.2 of a calorie. That's that change. So that's really a really tiny amount of energy. The other one is less than 1/10 of what is called of a calorie, or less than a kilojoule. So these changes on the -4 as it goes down, that change would give water the viscosity of acetone, like your fingernail polish remover, okay? And the positive one would make water have the viscosity of mercury, neither of which I think would work very well in any other systems that we're aware of, particularly in our bodies. So now let's see just how small or how many waters we're talking about when we're talking about some of these properties. I kind of like this sort of stuff a lot. Okay, imagine a teardrop. Okay, now these are like big teardrops. These are like the crocodile tears that a toddler, you know, the really big ones that come down there. Those have a volume of about 8 microliters, 8 to 10 microliters. Well, let's make it a really big one, so we're going to call it 10 microliters. So if we take a 10 microliter teardrop and measure its density at 22 degrees, which is 72 degrees, like room temperature, and we do the calculation of density times volume divided by molar mass times Avogadro's number, you're going to get 3.3353 times 10 to the 20th. That's a lot of zeros up there, but that's actually 333.53 quintillion. So the idea of what is quintillion? If each molecule represented a second, this would equate to 10 trillion years. A little less than 1 trillion years ago, 987 billion according to the Urantia bug, an associate force of organizers traveled out from Uversa and reported that the conditions were favorable for initiation of materialization in a certain sector of Orvonton. So if you take that as time, how much time that is, that's how many molecules are in that little teardrop that you saw going down your toddler's face of water, okay? So we're talking about things that are seriously tiny, very, very little, to give us a little perspective. I didn't put this up just because it was real colorful, but you'll see that there are 2 different structures up there, and we'll move forward. Science today conjectures that liquid water is actually 2 liquids, each containing water clusters in 2 different structures. And you see the expanded structure, I don't know if that is translating very well, or a closed structure. And this has to do with the different bond lengths. And they think the way that science today is looking at it, and each of these models only has 200 molecules. Remember, we're in a teardrop, we're looking at quintillion molecules. So this is a model using only around 200 molecules, and they're called clusters. And they really think that in your glass of water, that there's actually 2 different liquids going on in there, but they change all the time, and they cluster, and this explains some of the more anomalous properties of water is this clustering. And but we're talking about the water like this in your glass or you see in the river or falls out of the sky. But what about the water that's actually in our bodies? Does it actually cluster and look like that? One of the physiochemical facts of water is that it makes up about 50 or 60% of the human body. In an adult male weighing about 165 pounds, this is about 40 liters of fluid, with about 25 liters of this being inside your cells. This isn't what's like, in the extracellular spaces or in your stomach or other. This is actually what is inside the cell. In 2008, Philip Ball, who is both a really excellent physicist but a fantastic science journalist, posed a number of questions about the enduring mystery of water, and I highly recommend that you read his article. But one of the very intriguing ones that he asked is most of the water in cells structurally akin to the pure liquid at all? Like, does that look like that? So let's sort of explore that a little bit. This is a double helix. This is your DNA. This is what makes you you. So you can see the helical structure, I hope, which is represented by the gray bands and the blue bands, and you'll see the alpha helix. In a helix, if you're familiar with a helix, there's a groove, and in that groove is filled with water. That is what is in that groove. And actually, DNA in your cells have a sheath of water surrounding them, all around them, and it serves two really good purposes. One is it acts as a great insulator. It doesn't allow your DNA to become damaged by heat. That's kind of like, you drink a lot of liquid when you got a fever, is that you want to stay real hydrated and all that. Well, it's doing a lot of things, and one of them can be it's actually protecting your DNA a little bit, The other thing is that it protects it from UV damage. When you go underwater in the ocean, you don't worry about sunburn. It's only when you're out of the water that you have to worry about putting your sunscreen on, right? So it actually protects, water protects the DNA from being, which is very sensitive to UV. But water also participates in spontaneous mutations of our DNA. Now, spontaneous refers to the fact that the changes occur in the absence of chemical, radiation, or other environmental damage. Rather, they are usually caused by normal chemical reactions that go in the cell, such as hydrolysis. And hydrolysis is a general chemical term that refers to the modification of a compound when it interacts with water. These types of mutations or errors include depurination, which occurs when the bond connecting a purine to a deoxyribose sugar is broken by a molecule of water, resulting in a purine-free nucleotide that cannot act as a template during DNA replication, and also deamination, which results in the loss of an amino group from the nucleotide, again by the reaction of water. Most of these spontaneous errors, because every time it replicates, there's a lot of the ability of DNA to continually repair itself. However, bad news, folks, is that you get less of this as you get older. Okay, and so, but it is constantly repairing itself. But if it doesn't, even one of these spontaneous mutations that are caused with the interaction of water, if it doesn't get repaired, it becomes a mutation in your DNA, and it goes forward and it becomes a permanent mutation. This is much more closely to my discipline when you're looking at structures. This is The blue is a structure that was gained from crystallography of a protein that's called GRO-EL. And GRO-EL belongs to a class of proteins that are really rather amazing. They're called chaperonins or chaperones. They interact with other proteins to help them fold correctly. They help proteins move from one site to another. They help them in other processes that assist a protein to actually do its job. If you'll notice in here, the water is imposed on, that's what the red and whites are, is imposed upon the crystal structure. And actually in crystallography, knowing where the water is and when you're trying to figure out a structure is really very, very important, because it can change where your structure is, and it can actually, where you put the waters can define an active site or not. And so waters to crystallography is very seriously important. So the water with this particular type of protein, it can do many things. With the hydrogen bonding, it can help. It can connect with the water on another protein and bring it closer to the chaperone, so that the chaperone can help it do its job. There's many ways that water can cover things, and then it can go away and expose things. And so water plays a very important role in particularly with chaperones. But neither this water or the water associated with the DNA bear any resemblance to that water that we saw that's in the glass. But remember that even all the water that we've been talking about and all the pictures that you saw, you had the red ball and you had the two hydrogens. So the covalent bonds are still there. And so the dipole that we talked about earlier is still present in the molecule. But now let's move to something that's seriously exciting. We're going to move to some very recent research that was done in 2016 and 2017 at Oak Ridge National Lab in Tennessee, and was also reproduced in Germany, which demonstrates a behavior that water can demonstrate, a behavior called quantum tunneling. But first we need to understand what quantum tunneling is. I'm not a physicist, but I'll do my best to try to explain quantum tunneling. Quantum tunneling falls under the domain of quantum mechanics, the study of what happens at the quantum scale. This process cannot be directly perceived, but much of its understanding is shaped by the microscopic world, which classical mechanics cannot adequately explain. To understand the phenomenon, particles attempting to travel between potential barriers, sorry, I need to get a little bit of sip of water. To understand the phenomenon, particles attempting to travel between potential barriers can be compared to a ball trying to roll over a hill. Quantum mechanics and classical mechanics differ in their treatment of this scenario. Classical mechanics predicts that particles that do not have enough energy to classically surmount a barrier will not be able to reach the other side. Thus, a ball without sufficient energy to surmount the hill would roll back down, or lacking the energy to penetrate a wall, it would either bounce back, as in reflection, or in the extreme cases, it would bury itself inside the wall, which is called absorption. In quantum mechanics, these particles can, with a very small probability, tunnel to the other side, thus crossing the barrier. Here, the barrier could, in a sense, borrow energy from its surroundings to tunnel through the wall or roll over the hill, paying it back by making the reflected particles more energetic than they otherwise would have been. The reason for this difference comes from the treatment of matter in quantum mechanics as having properties of waves and particles. One interpretation of this duality involves the Heisenberg uncertainty principle, which defines a limit on how precisely the position and momentum of a particle can be known at the same time. This implies that there are no solutions with a probability of exactly 0. Though a solution may approach infinity. For example, the calculation for its position was taking as a probability of 1. The other is that its speed would have to be infinity. So this particular diagram, this is a probability wave, and as you see, it moves and it approaches the barrier. Some of the energy is absorbed and it stays within the barrier, but some of it, a tiny amount of it, the probability that it will be, and that's that tiny amount that they're talking about, is on the other side, and that's what the little red amount is on the other side, and you'll see that the probability wave is much reduced to the other, but it's still a probability that it is going to be over there, okay? So I'm going to show you two different animations to kind of demonstrate this. Now, we're talking about particles here. We're talking about electrons or photons or something like that. We're not talking about a molecule. Okay, we're talking that. So let's go and see if we can. Okay, so see, it approaches the barrier and then it reflects back, but some of it manages. Now, that barrier is not very thick and it's not a huge one. It's not a lot to overcome, right? Okay, but let's look at another one that is a little bit. I hope y'all can see that one. Do you see? This is more of like a photon, example of a photon. As it approaches the barrier, it magically goes through the invisibility cloak or something. You know, it magically goes through the wall. And so this is what quantum mechanics is. This is what quantum tunneling is all about. Just as a little sort of aside, which I thought was fascinating, is the quantum tunneling is the reason that a microchip in your computer can only be so small, because it has no ability to continue when it gets down to it's at a finite size, because after a point the electrons are going to tunnel and they're going to go around it, and it's not going to be able to contain it on the chip, and so that's a problem. And so quantum tunneling is actually a problem that people deal with in microchips a lot, and but we're talking more about particles and like electrons and things like that. So what does this have to do with water? It's a molecule made up of 3 atoms. You know, it's got a lot of electrons. It's got, neutrons. It's got those. So why are we saying that it can display tunneling behavior? This is like the neatest experiment. Okay, this experiment that was done at Oak Ridge, there's this material that's called beryl, which is kin to the stone like an emerald or an aquamarine in your jewelry. Okay, and these types of stones have very tiny channels in them, and the beryl stone is just large enough to let one molecule of water go down the channel, and it's a 6-sided channel. Let me see if I can put a. No, we're gonna see if I can get something up here to help us talk about it. You'll see that it's got like 6 sides to this channel. You see the 6 different sides here. This is the actual beryl stone, the red and the green and some of the yellow. This is the representation of the water. The oxygen is where my pointer is right now. And, each water has 2 hydrogens. Well, these turquoise balls are the representation of the probability of where the hydrogen is at any particular point in time of just one of the hydrogens, okay? The other hydrogen, is kind of hard to say here, is actually on the other side of that one, so it forms like almost two rings around the hydrogen. Now, with this probability, it's obviously the molecule loses its dipole because it no longer has that angle that causes it to be positive, so it loses the dipole charge, more negative on one and positive on the other, as it moves down the channel, or as it is in the channel. The diagram on the right is a probability diagram of where the actual hydrogens are at any particular point in time. And the blue is where the hydrogens will never be. And the pink going to red is there's more probability that they could occupy that particular site. But the yellow is where they are, okay? And so instead of being two discrete, or being a discrete hydrogen, the probability that it can fill anywhere at that space at any particular point in time. And so what they, let me get the other back up here. So they showed that this molecule of water, by using this tunneling effect, it can crawl down this channel. It can move itself as it goes down the channel. And so now you've got a molecule acting like a particle, and where we don't have explanations of things that go on, and we don't in some cases, in cell membranes, and particularly when proteins are inserted into membranes. Water, we know, plays a big part in that. We think that this tunneling effect by water may be part and may have huge implications in these areas of physiology and cell physiology, and explanations of things that we really can't understand, how water gets to where it actually does what it does. And so when they displayed this phenomenon, everybody, it was huge news in the whole community of water people and cell folks, as that it may be the ability to explain things that we just don't have, we have not had a really good solid explanation for. So now water has entered the quantum age and displays a new talent, something we never knew that it had, okay? But it certainly does not look or behave like the water in Bruce's glass, okay? So so we've sort of expanded our knowledge of water. So now let's move on. So in 2019, the scientific database on liquid water has multiplied many-fold since the 1930s. Yet both materialistic philosophy and mechanistic cosmology still persistently develop, and in many instances heavily influence the scientific endeavor. Today, materialism is often referred to as physicalism, to separate it as a philosophical discipline from the social economic connotation of avarice and greed. The old matter is the fundamental substance of nature has given way to all things, including mental states and consciousness, are the result of material interactions. Materialism and physicalism remain reductionist and perhaps even more deterministic. This can be imagined by explaining thought, behavior, consciousness, emotion, experience, memory as a manifestation of neurochemical processes within certain regions of the brain tissue, which are made up of highly evolved cells. The reduction argument can be advanced to the molecular level of enzymes, neurotransmitters, hormones, etc., and then further to the atomic quantum level of hydrogen bonds, protein donors, acceptors, energy transport. becoming even more deterministic when invoking causality, such as in cause and effect in areas like physics, chemistry, genetics, evolution, as in this mutation causes this disease, this chemical reaction results in this product, this environmental pressure causes this adaptation. Sometimes it's kind of clarifying to look at extremes, to know where you might want to be in the middle. There is actually a very radical form of materialism extant today. It is espoused by two very well-known Canadian philosophers, Paul and Patricia Churchland, and it's called Eliminative Materialism. And I found this description in the Stanford Philosophical Encyclopedia pretty startling. So I'm going to read this one to you. Just as we came to understand that there are no such thing as demons, because nothing at all like demons appear in modern accounts of strange behavior, so too eliminative materialists argue that various folk psychology concepts, like our concept of belief, will eventually be recognized as empty posits that fail to correspond with anything that actually exists. Since there is nothing that has the causal and semantic properties we attribute to beliefs and many other mental states, it will turn out that there really are no such things. I found that pretty startling myself, but anyway. And though not considered necessarily radical, there is mechanistic cosmology. There is a mechanistic cosmology taken to an extreme, and we're probably all very familiar with. Mechanistic cosmology pursued to a logical, though arguably hypothetical conclusion, will or would produce the elusive toe, theory of everything, or a grand unified theory. This is when all physical aspects of the universe would be explained and linked in one all-encompassing coherent framework. And this is considered one of, if not the most, major questions in physics even today. Let's back up in history just a little bit. In 1913, at the age of 35, a man named Lawrence Joseph Henderson, who was a physiologist, a chemist, a philosopher, and a sociologist, published a book, The Fitness of the Environment, an inquiry into the biological significance of the properties of matter. In this book, Henderson discusses a number of things, but he discusses a lot about water, an enormous amount about water in this book. And I got us a copy of this book, and I'm going to read you the last sentence in his book. For the whole evolutionary process, both cosmic and organic, is one, and the biologist may now rightly regard the universe in its very essence as biocentric. This was the first statement of what would become the finely tuned universe hypothesis or theorem. It would languish until 1961, when Robert Dicke, a physicist, noted that physical phenomenon as gravity and electromagnetism, if only slightly different, weaker or stronger, life as we recognize it would not exist. Fred Hoyle in 1981 wrote The Intelligent Universe, where he was mainly looking at the carbon cycle but came to the same conclusion. And then John Gribben and Martin Rees in 1989 wrote Cosmic Coincidence, that went on to discuss a number of other physical phenomena that are very finely tuned. And I'll give you three examples. The ratio of the strength of electromagnetism to the strength of gravity for a pair of protons. The cosmological constant. The number of spatial dimensions in space-time. Gribben actually Reese actually puts forth a really good article about how life, if we had 2 or 4 dimensions, could not exist physically. Then there's others that have, fine-tuned this and offered, and then there are, of course, the people that have tried to offer counters to it, and such as what is referred to as the weak anthropic principle. But the big one that everybody knows is the multi-universe hypothesis of Everett, to counter this idea that the universe that we live in is very, very finely tuned for life. Even people that are really mechanists still can't, they find this very intriguing. In his 1988 book, A Brief History of Time, Stephen Hawking wrote, "The laws of science as we know them at present contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life." So from 1855 until the 1930s, what was not being understood about liquid water? Perhaps Henderson was that unknown beacon when he talked about water and put forth his principle in this book. He noticed the connection between the small, anomalous, ubiquitous molecule, liquid water, and life. As students of the Urantia book, we've all become familiar with the triads that are found throughout the papers, such as truth, beauty, and goodness in my title. Though a very teleological assessment, I propose the addition of another triad to the list: water, life, survival. The truth of water is all the material facts that have been and will be discovered about it. The beauty of water is that water is essential to life on this planet. The goodness of water is that this life gives the opportunity for the eternal adventure, survival. I'd like to thank my friends Jeff Waddles and Phil Rolnick for much needed philosophical advice and encouragement. My friends Mo and Nancy Davis, who are also students of the Urantia book, who assisted in preparing this presentation, and my friends Patricia Clem and Dee Dee Nicolau for their friendship and encouragement in this project. And now we can start our discussion. Thank you.